In this video, we briefly introduce the low-in-band RCS circularly polarized microstrip antenna array, without using metasurfaces or changing the shape of the antenna. The independent regulation of the radiation and scattering performance is realized only through the feed network. The relevant work can be found in IEEE transactions on antennas and propagation. Circularly polarized antennas have been widely used in satellite communications and data link systems. However, simultaneously achieving a low radar cross-section and high radiation performance for a CP antenna is difficult. In the past few years, several methods have been proposed to reduce the RCS of CP, such as loading metasurfaces around or above the antenna and exciting low-scattering metasurface as a radiator. However, these methods will increase the profile and complexity of the antenna or deteriorate the aperture efficiency of antenna. Compared with the conventional feed network of array antenna, CP antenna we propose is composed by different across two antenna arrays, which load to different feed networks, named Feed Network A and Feed Network B. In our designing, the 3 dB branch line coupler is introduced. Because of the high isolation between the input and isolation ports of the 3 dB branch line coupler, the radiated energy does not pass through the feed network, and radiation and scattering energy will not affect with each other. The isolation port of the 3 dB branch line coupler was connected to another 3 dB branch line coupler located at the diagonal of the two crossed separate through a microstrip line. Two 180 degrees phase shifting loads are introduced on the two connecting microstrip lines, forming the wideband feed network A. The feed network B is formed by rotating wideband feed network A around the subarray center by 90 degrees. The principle behind this is that each connecting line of feed network B introduces an additional 180 degrees phase shift relative to feed network A. Based on this design, subarray A and subarray B exhibit similar radiation characteristics and scatter a phase difference of 180 degrees under any linearly polarized incident wave. This enables scatter cancellation and thus reduces the overall RCS of the antenna. The proposed CP antenna array is fabricated and measured. The results show that it has broadband impedance and axial ratio characteristics. Compared with the reference antenna array, the in-band monostatic RCS was significantly reduced to 3 to 5.4 GHz under X and Y polarized incident waves, with a maximum reduction value of 19.2 and 20.18 dB, respectively. Because of its good CP radiation performance and low in-band RCS characteristics, the proposed antenna array is a good candidate for low observability platforms.
Low in-band RCS reconfigurable metasurface with LP feed for CP transmission, LP reflection, and simultaneous transmission reflection mode switching. Let's divide into the outline of our presentation. The vision of 6G technology is to integrate satellite and ground communications seamlessly. To achieve this, we've turned to reconfigurable transmission reflection integrated metasurfaces, which enable multi-beam communication. A key requirement is the ability to switch between linearly polarized and circularly polarized beams for ground and satellite communications, respectively. Now, let's discuss the meta-atom design. Our metasurface features a receiving patch for linear polarization and a transmitting patch for circular polarization, enabling LPCP transmission. The receiving layer is divided into two parts for X-pole and Y-pole patches. We've integrated 2-pin diodes on X-pole to achieve 1-bit phase control for reflection and transmission modes. We've achieved variable-sized 1-bit reflection phase control by introducing rectangular branches in Y-pole. 1-bit reflection phase bandwidth is 10.8% in Y-pole. 1-bit reflection phase bandwidth is 12.9% in X-pole. 1-bit LPSP transmission covering is 3.5%. We've constructed a 12 by 12 array with a unit period of 15 millimeters. This array is excited by an LP horn and operates with an F/D ratio of 0.8. Our RTRA metasurface operates in 3 modes: RA mode, TA mode, and TRA mode. To enhance the array's performance, we've implemented the random sequential rotation technique, or RSRT, which improves the array's bandwidth and radiation characteristics during large-angle scanning. In this slide, you can see the RSRT for the transmitting layer and phase distribution in TA mode for zero scanning. TRA mode unit distribution and phase distribution when the RA and TA beams are pointed at 0 and 30, respectively. the checkerboard distribution, and the encoding for zero beam pointing in the RA mode for RCS reduction. We've also achieved plus or minus 60 degrees beam scanning in both RA and TA modes, which is quite an achievement for our metasurface. Measure results in TRA mode, such as RA, 0 and TA, 150 and so on. Let's take a look at some measured results. We've achieved a 1 dB gain bandwidth of 10.1 to 11.3 GHz and 10.45 to 11.05 GHz in the RA and TA modes, with an aperture efficiency of 19% and 13%, respectively. The 3 dB axial ratio bandwidth is impressive, covering 9.87 to 10.95 GHz in the ZOS plane and 9.83 to 10.7 GHz in the OS plane. In conclusion, our RTRA metasurface not only achieves plus or minus 60 degrees beam scanning in both RA and TA modes, but also improves the axial ratio bandwidth using our SRT. By employing genetic algorithms, we've obtained simultaneous beam scanning for both RA and TA. The proposed RTRA, arranged in a checkerboard pattern, also exhibits in-band RCS reduction characteristics. Thank you for your attention. If you have any questions or would like to collaborate on future projects, please reach out to our email.
Hello everyone, it's my pleasure to share our latest work on a dual-polarized, leading-edge wing conformal, tightly coupled dipole array, LECTCDA, with enhanced low-scattering characteristics. First, let me outline the challenge. For next-generation aircraft, embedding antennas seamlessly into the wing's leading edge offers significant advantages in terms of integration and aerodynamics. However, the stringent curvature constraints introduce two major challenges. First, large curvature tends to degrade gain and impedance bandwidth. Second, achieving a low scattering design on a curved surface, especially one involving absorptive structure, is particularly difficult. Our goal was to tackle both challenges simultaneously. Our solution builds on tightly coupled dipole arrays for their proven wideband and wide scanning capability. A scattering matrix-based design process was employed to transform planar TCDA elements into a conformal geometry defined by a parabolic leading-edge surface. This approach allowed us to efficiently simulate and compensate for the curvature-induced gain loss by fine-tuning key parameters including coupling width, WAIM thickness, and ground plane profile, until the performance of the conformal array satisfied the specified requirements. For RCS control, a flexible, broadband ITO absorber was integrated onto the WAIM layer. Starting from an octagonal ring resonator, we inwardly concaved the corners to extend the current paths and introduced notches to fine-tune the high-frequency absorption. The final resistive meta-absorber achieves better than 10 dB absorption from 6 to 18 GHz, while maintaining stable performance over a relatively wide angular range without noticeably degrading the in-band radiation characteristics. We fabricated a 10 by 1 prototype using standard PCB for the dipoles, resin 3D printing for the WAIM and supporting structures, and metal 3D printing for the ground structures. Measured results confirm a 4:1 impedance bandwidth and plus or minus 45 degrees scan range with VSWR less than 3.5 for both horizontal and vertical polarizations. The peak broadside gains remain high across the band, and cross-polar isolation remains above 15 dB. Most notably, our RCS tests conducted in a compact-range chamber show an average reduction of 41.7 dB for H-pole and 35.1 dB for V-pole incidence when compared to a bare metal wing of the same shape. Moreover, we experimentally confirmed a significant improvement over a reference array without the ITO layer. In summary, our design combines ultra-wideband, dual polarization scanning performance with good low scattering performances on a large curvature wing leading edge. We believe this design opens a new path for the development of low scattering, conformal RF systems for next-generation aircraft. Thank you for your attention.